Tonight, we begin a journey toward one of the biggest questions humanity has ever asked. How many galaxies are there in the universe? At first, it sounds like a question that should have a simple answer. We know how many planets orbit the Sun. We know how many major moons circle Jupiter. So surely we should be able to count galaxies as well. But the moment we try, we run into a strange problem. Every galaxy we can count is only a galaxy we can see. Beyond the reach of our telescopes may lie countless others, too faint, too distant, or hidden behind cosmic dust. The deeper we look into space, the more galaxies appear. Every generation of astronomers has discovered that the universe is larger and more crowded than anyone previously imagined. By the end of this journey, you'll understand why even today we cannot give a single exact number for the galaxies in the cosmos, and why that uncertainty is one of the most fascinating mysteries in all of science. Imagine stepping outside on a perfectly clear night, far away from city lights. The sky above you is dark and endless. Thousands of stars shine overhead. To most people, that seems like an enormous number. Yet those few thousand visible stars represent only the tiniest fraction of what exists. Every star you can see with your naked eye belongs to our own galaxy, the Milky Way. Every constellation ever named by ancient civilizations, every bright star sailors used for navigation, every planet visible without a telescope, all of them exist within this single vast structure. The Milky Way itself contains hundreds of billions of stars, yet to our eyes, it appears only as a pale band of light stretching across the heavens. For thousands of years, people did not know what that glowing band really was. Different cultures created myths and legends to explain it. Some imagined it as a heavenly river. Others saw it as a road used by spirits and gods. Still others believed it was milk spilled across the sky by divine beings. No one realized that this mysterious glow was actually the combined light of countless distant stars, packed together so densely that the human eye could not separate them. The truth remained hidden because our eyes simply were not powerful enough to reveal it. Yet even without a telescope, there is something remarkable you can see. On the darkest nights, if you know exactly where to look, you can spot a faint, blurry patch in the constellation Andromeda. Most people would never notice it. It looks insignificant, a tiny smudge against the darkness. But that faint blur is the Andromeda Galaxy, an entire galaxy containing roughly 1 trillion stars. The light entering your eyes from Andromeda has been traveling through space for about 2.5 million years. When that light began its journey, modern human civilization did not exist. You are seeing a galaxy as it appeared long before any city was built, long before any written language existed. It is the most distant object visible to the unaided human eye. In the southern hemisphere, observers can see 2 more faint patches known as the Large and Small Magellanic Clouds. For centuries, sailors used them as landmarks while navigating the oceans. They appeared to be detached fragments of the Milky Way. Only much later did astronomers realize that these glowing clouds were actually separate galaxies orbiting our own. These were the only galaxies humanity could see without technological assistance, and because they looked so small and insignificant, most people never imagined what they truly were. This explains why nearly all ancient civilizations believed the Milky Way was the entire universe. It wasn't arrogance, it wasn't ignorance, it was simply the most reasonable conclusion based on the evidence available. Every visible star belonged to the Milky Way. Beyond that glowing band seemed to be nothing but darkness. There was no reason to suspect that countless other galaxies might exist far beyond our own. Everything began to change with one invention, the telescope. When Galileo Galilei turned one of the first telescopes toward the Milky Way in the early 17th century, he made a discovery that forever changed humanity's view of the cosmos. Under magnification, the hazy band of light dissolved into countless individual stars. What had appeared to be a glowing cloud was actually a vast collection of distant suns. The Milky Way was not a misty structure, it was a galaxy made of stars. This revelation was only the beginning. As telescopes improved, astronomers noticed strange objects scattered throughout the... Astronomers catalogued more and more of these mysterious spirals. One of the most famous catalogues was created by Charles Messier, a comet hunter who became frustrated by constantly confusing these fuzzy objects with the comets he was searching for. To avoid wasting time, he compiled a list of every object that was definitely not a comet. Ironically, this catalogue would later become one of the most important collections in astronomy. Many of the objects Messier wanted to ignore turned out to be some of the most spectacular structures in the universe. At the same time, astronomers William Herschel and Caroline Herschel attempted something even more ambitious. They tried to map the shape of the Milky Way itself by counting stars in different directions. Their work revealed that our galaxy was a vast, flattened system of stars, and that the Sun occupied only a small region within it. For the first time, humanity understood that it lived inside a gigantic cosmic structure rather than beneath a dome of stars. Yet one mystery remained unsolved. What exactly were the spiral nebulae? Some astronomers believed they were relatively small objects located inside the Milky Way. Others proposed a much more radical possibility. Perhaps these spirals were entire galaxies beyond our own, vast collections of stars separated from us by unimaginable distances. They called these hypothetical objects island universes. The difference between these two ideas was enormous. If the spirals existed within the Milky Way, then our galaxy might truly be the entire universe. But if the spirals were separate galaxies, then the Milky Way would be only one among countless others scattered across a much larger cosmos. The question remained unanswered because astronomers lacked the most important piece of information: distance. Without knowing how far away the spirals were, nobody could determine their true size or nature. By the early 20th century, this disagreement had grown into one of the greatest debates in astronomy. Scientists argued passionately on both sides. Some claimed the spirals must be nearby because they appeared to change too quickly to be enormous galaxies. Others pointed out evidence suggesting they lay far beyond the boundaries of the Milky Way. The argument continued for years because neither side possessed definitive proof. The breakthrough came from a young astronomer named Edwin Hubble. Using one of the largest telescopes in the world, Hubble studied the Andromeda spiral in extraordinary detail. Within it, he discovered a special type of star known as a Cepheid variable. These stars brighten and dim in a regular rhythm. Astronomers had already learned something remarkable about them. The length of their pulsation directly reveals their true brightness. This relationship gave Hubble a powerful tool. If he knew how bright a Cepheid truly was, and measured how bright it appeared from Earth, he could calculate its distance. A bright star that looks dim must be very far away. A bright star that still appears bright must be relatively close. Using this method, Hubble determined the distance to Andromeda. The result changed everything. Andromeda was not inside the Milky Way. It was far beyond it. The distance was so great that Andromeda could only be another galaxy entirely, a separate island universe filled with stars of its own. In a single measurement, humanity's understanding of reality expanded dramatically. The Milky Way was no longer the universe, it was merely one galaxy among many. Suddenly, every spiral nebula in the sky took on a new meaning. Those faint fuzzy patches were not clouds. They were galaxies, entire galaxies, each containing billions or even trillions of stars. The universe became vastly larger than anyone had imagined. And with that discovery came a new question. If Andromeda is another galaxy, and if thousands of other spirals are galaxies too, then how many galaxies exist in the universe altogether? That question would lead astronomers into one of the greatest cosmic investigations ever undertaken. The discovery that Andromeda was a separate galaxy did far more than settle an argument. It completely transformed humanity's place in the cosmos. For thousands of years, people had believed that the Milky Way was everything. Then, almost overnight, our galaxy was reduced from the entire universe to just one member of a much larger family. Every spiral nebula that astronomers had catalogued suddenly became something extraordinary. They were no longer clouds floating inside our galaxy. They were galaxies themselves, each one containing billions or even trillions of stars. Imagine what that realization felt like. It was as if humanity had spent its entire existence believing it lived on the only island in the world, only to discover that the ocean was filled with countless other continents stretching far beyond the horizon. The universe had expanded in size beyond anything anyone had previously imagined, but Edwin Hubble was not finished reshaping our understanding of reality. Once astronomers accepted that galaxies existed beyond the Milky Way, a new question emerged. If these galaxies were scattered throughout space, what were they doing? Were they stationary? Were they moving randomly? Or was there some larger pattern hidden within their motions? To answer this question, astronomers began studying the light coming from distant galaxies. Every galaxy emits light from billions of stars. By spreading that light into a spectrum, scientists could analyze its properties in remarkable detail. What they discovered was astonishing. The light from most galaxies was shifted toward the red end of the spectrum. This effect became known as redshift. To understand redshift, imagine an ambulance racing down a street. As it approaches you, the sound waves become compressed and the siren seems higher in pitch. As it moves away, the sound waves stretch out and the pitch becomes lower. Light behaves in a similar way. When an object moves away from us, its light waves become stretched, shifting toward longer and redder wavelengths. Astronomers expected some galaxies to move toward us and some to move away. Instead, they found something far stranger. Almost every galaxy appeared to be receding. No matter where astronomers looked in the sky, galaxies seemed to be moving away from Earth. Even more remarkable, the farther away a galaxy was, the faster it appeared to be retreating. This relationship became one of the most important discoveries in the history of science. At first glance, it sounded as though Earth occupied the center of a gigantic explosion, but that interpretation was completely wrong. The galaxies were not flying through space away from a central point. Instead, space itself was expanding. A useful analogy is a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. No raisin sits at the center of the expansion. The space between them simply grows larger. The universe behaves in much the same way. Galaxies are carried apart because the fabric of space itself is stretching. The more distant a galaxy is, the more space exists between us and it, and therefore the faster it appears to recede. This discovery revealed that the universe was not static and eternal. It was changing. It was growing. And if the universe is expanding today, then running time backward suggests that it must once have been smaller, denser, and hotter. This insight eventually led to the development of the Big Bang theory, the idea that the observable universe began around 13.8 billion years ago from an extremely hot and dense state. For our story, however, the expanding universe provided another crucial tool. Redshift became a cosmic ruler. By measuring how much a galaxy's light had been stretched, astronomers could estimate how far away it was. The greater the redshift, the farther the galaxy. This method became one of the higher rungs on what astronomers call the cosmic distance ladder. The cosmic distance ladder is one of the most ingenious achievements in science. No single technique can measure every distance in the universe. Instead, astronomers use a chain of overlapping methods, each one extending slightly farther than the previous one. The first rung involves nearby stars. As Earth travels around the Sun, nearby stars appear to shift slightly against the background of more distant stars. This tiny change in position is known as parallax. By measuring it carefully, astronomers can determine the distances to stars within our galactic neighbourhood. Beyond that range, parallax becomes too small to detect. Astronomers then rely on stars like the Cepheid variables that Hubble used in Andromeda. Because their pulsation periods reveal their true brightness, they serve as reliable distance markers across nearby galaxies. Farther still, even Cepheid stars become too faint to observe. At those enormous distances, astronomers turn to another tool, supernovae. Certain types of exploding stars reach nearly identical peak brightness. Because their true luminosity is known, they act like enormous cosmic lighthouses visible across billions of light years. By comparing their actual brightness to their apparent brightness, astronomers can calculate distances on truly staggering scales. Beyond even those distances lies redshift itself. By combining all these methods together, astronomers gradually built a map extending outward across the observable universe. For the first time in history, humanity possessed the tools necessary to explore the cosmos on its largest scales. Yet another problem remained. Even though astronomers could now measure distances, they still could not answer the question that brought us here tonight. How many galaxies are there? The difficulty was simple. Telescopes can only see so far. For decades, astronomers counted the galaxies visible through their instruments. But those galaxies represented only the brightest and closest members of a much larger population. Beyond the limits of observation stretched an enormous darkness. No one knew what was hiding there. Was it empty? Or was it filled with galaxies too faint to detect? The answer would require an entirely new generation of technology. That technology arrived in 1990 with the launch of the Hubble Space Telescope. Unlike ground-based observatories, Hubble orbited above Earth's atmosphere. Atmospheric turbulence no longer blurred its vision. For the first time, astronomers possessed a telescope capable of observing the universe with extraordinary clarity. Hubble quickly began producing breathtaking images. It photographed galaxies colliding. It captured stars being born inside giant clouds of gas. It revealed structures throughout the universe in unprecedented detail. But one of the telescope's most important achievements began with an idea that many astronomers considered completely absurd. The proposal came from astronomer Robert Williams, who served as director of the Space Telescope Science Institute. His suggestion sounded almost irresponsible. He wanted to point the world's most valuable telescope toward a patch of sky where there appeared to be absolutely nothing. No bright stars, no known galaxies, no interesting objects, just darkness. The target region was incredibly tiny. If you held a grain of sand at arm's length against the night sky, it would cover approximately the same area. Most astronomers assumed that observing such a patch would be a waste of precious telescope time. Hubble was in enormous demand. Researchers competed fiercely for every available hour of observation. Why spend days staring at emptiness? Yet Williams believed that apparent emptiness might conceal something extraordinary. So Hubble was directed toward that tiny dark patch, and it stared, hour after hour, day after day. For 10 straight days, the telescope collected every faint photon arriving from that small region of sky. The longer it observed, the deeper it could see. Light that would normally be too faint to register slowly accumulated on Hubble's detectors. When the final image was assembled, astronomers were stunned. The supposedly empty patch was not empty at all. It was overflowing with galaxies, thousands of them. Roughly 3,000 galaxies appeared in a region of sky so small that it seemed almost insignificant. Some were spirals resembling the Milky Way. Others were giant elliptical galaxies. Still others possessed strange, distorted shapes, unlike anything nearby. Many of them were so distant that their light had been traveling toward Earth for billions of years. The image became known as the Hubble Deep Field, and it fundamentally changed astronomy. The implications were impossible to ignore. If a tiny patch of sky containing no obvious objects could reveal 3,000 galaxies when observed deeply enough, what would happen if similar observations were made elsewhere? Suddenly, darkness no longer looked empty. Darkness looked crowded. The universe appeared far richer than anyone had imagined. The Hubble Deep Field was more than a photograph. It was a time machine. Because light requires time to travel, looking farther into space means looking farther into the past. Some galaxies in the image appeared relatively nearby. Others were seen as they existed billions of years ago. The faintest and most distant objects revealed the universe during its youth. In a single picture, astronomers could see multiple eras of cosmic history simultaneously. The image was not merely showing distant galaxies, it was showing the evolution of the universe itself. The reaction throughout the scientific community was immediate. A region once assumed to be empty had become one of the most important observations in the history of astronomy. It confirmed something profound. The universe was not sparsely populated, it was densely packed with galaxies, stretching in every direction. And if one tiny patch contained thousands of galaxies, then the total number across the entire sky must be enormous. The question was no longer whether galaxies were common. The question was just how many there truly were. Astronomers now had a strategy. Count the galaxies in a small area. Measure exactly how much of the sky that area represents, then multiply. It seemed straightforward, but the answer would prove more surprising than anyone expected. Because the deeper astronomers looked, the more galaxies they found, and there was no sign that the discoveries were coming to an end. The universe was beginning to reveal itself as something far larger, far older, and far more crowded than even Hubble could have imagined. And soon, an even deeper look into the darkness would change the numbers again. When the Hubble Deep Field image was released, astronomers around the world were stunned. A patch of sky chosen specifically because it appeared empty had turned out to contain thousands of galaxies. But science has a habit of asking one question immediately after answering another. If 10 days of observation could reveal roughly 3,000 galaxies in a tiny patch of darkness, what would happen if astronomers looked even deeper? What would appear if they collected even more light? Would they eventually reach a limit where the galaxies stopped? Or would the universe continue revealing more and more structures hidden in the dark? These questions drove astronomers to push Hubble beyond anything it had done before. They selected another tiny region of sky, this time in the southern constellation Fornax, and began one of the most ambitious observing campaigns ever attempted. Over many months, the telescope repeatedly returned to the same location, gathering every faint photon that arrived from that direction. The resulting image became known as the Hubble Ultra Deep Field, and when scientists finally processed the data, they found something extraordinary. In a region of sky no larger than a grain of sand held at arm's length, Hubble revealed around 10,000 galaxies. 10,000 entire galaxies packed into a patch of apparent nothingness. The ultra-deep field did more than increase the galaxy count. It transformed the image into a journey through time. Some galaxies appeared relatively close, displaying familiar spiral structures like those found in the modern universe. Others looked distorted, chaotic, and irregular. These strange shapes were galaxies seen during their youth, before billions of years of cosmic evolution had shaped them into the elegant structures we observe today. Many of the faintest galaxies in the image were so distant that their light began its journey when the universe was only a small fraction of its current age. Looking at the ultra-deep field was like opening a history book written in light. Every point represented not only a galaxy, but also a different moment in cosmic history. Astronomers soon realized that the universe was even more crowded than they had believed. Every time they increased the sensitivity of their observations, new galaxies emerged from the darkness. It was as if the cosmos contained layers hidden beneath layers, waiting for better instruments to reveal them. Yet there was another problem. Even the most powerful telescope cannot see everything. Many galaxies are simply too faint. Some are so small and distant that their light is spread out over enormous stretches of space, making them nearly impossible to detect. Others are hidden behind brighter foreground objects. If astronomers wanted to estimate the true number of galaxies, they would need a way to account for those that remained invisible. Nature itself provided an unexpected solution. According to Einstein's theory of general relativity, massive objects bend the fabric of space-time. Light traveling through this curved space follows a bent path. When a massive cluster of galaxies lies between Earth and a much more distant galaxy, the cluster's gravity acts like a gigantic cosmic lens. It bends and magnifies the light of the background galaxy, making it appear brighter than it otherwise would. This phenomenon is called gravitational lensing. By using galaxy clusters as natural magnifying glasses, astronomers were able to detect galaxies that would normally remain hidden beyond the reach of their telescopes. Some of the earliest and most distant galaxies ever observed were discovered through this technique. Their light had travelled for billions of years before being bent and amplified by a foreground cluster, allowing humanity to glimpse objects from the dawn of cosmic history. As observations accumulated, astronomers began performing a simple but powerful calculation. If one tiny patch of sky contained thousands of galaxies, how many galaxies would exist across the entire celestial sphere? The answer required multiplying the number of galaxies found in deep field images by the number of similar patches needed to cover the whole sky. When researchers performed this calculation, they arrived at the first widely accepted estimate. The observable universe appeared to contain somewhere between 100 billion and 200 billion galaxies. The number was staggering. These were not stars, these were galaxies, each containing millions, billions, or even trillions of stars of its own. Even the lower estimate represented a cosmos so vast that ordinary human intuition struggled to comprehend it. For years, this figure became the standard answer. Documentaries repeated it, textbooks printed it, scientists referenced it. The observable universe seemed to contain roughly 200 billion galaxies. Yet hidden within that estimate was a critical limitation. The deep field images only counted galaxies bright enough to be detected. They could not include the countless galaxies whose light remained below the threshold of observation. The number represented what humanity could see, not necessarily what actually existed. The distinction would become one of the most important questions in modern cosmology. In 2016, a team of astronomers led by Christopher Consolis decided to revisit the galaxy counting problem from a completely different perspective. Rather than simply counting the galaxies visible in telescope images, they asked a deeper question. How many galaxies should exist if our understanding of cosmic evolution is correct? To answer this, they transformed deep field observations into three-dimensional maps of the universe. Galaxies were organized not only by position, but also by distance, which meant they were effectively organized by time. Because light takes time to travel, looking farther into space means looking farther into the past. This allowed astronomers to compare the galaxy population across different eras of cosmic history. What they found was remarkable. The early universe appeared to contain far more small galaxies than the modern universe does today. This made sense when viewed through the lens of cosmic evolution. Galaxies are not static objects. Over billions of years, they collide, merge, and grow. Small galaxies frequently combine to form larger ones. As a result, many of the tiny galaxies that existed in the distant past have long since disappeared as separate objects, becoming part of larger galaxies. The modern universe therefore contains fewer individual galaxies than the young universe once did. By modeling this process and accounting for faint galaxies hidden below the detection limits of current telescopes, the team arrived at a surprising conclusion. Approximately 90% of all galaxies might be invisible to us. This result dramatically changed the estimated galaxy count. Instead of 200 billion galaxies, the observable universe might contain around 2 trillion galaxies. The difference was enormous. A 2 followed by 12 zeros. 2,000 billion galaxies. The universe suddenly seemed 10 times more crowded than previous estimates suggested. Every visible galaxy might be accompanied by many more hidden in the darkness, too faint for any current instrument to detect. The discovery captured public attention because it transformed the scale of the cosmos once again. Just when humanity thought it had grasped the magnitude of the universe, the numbers expanded dramatically. Yet science rarely allows certainty to last for long. Only a few years later, another line of evidence began pointing toward a very different answer. The source of this new evidence was not a giant telescope, but a spacecraft traveling through the outer solar system. New Horizons, famous for providing humanity's first close-up views of Pluto, had continued its journey far beyond the planets. Out there, in the cold darkness beyond much of the solar system's dust, New Horizons occupied one of the darkest observing locations ever reached by a human-made object. This unique position gave astronomers an opportunity that had never existed before. Near Earth, measurements of the faint cosmic background are contaminated by zodiacal light, a glow produced when sunlight scatters off countless dust particles drifting through the inner solar system. This glow is brighter than many of the signals astronomers wish to study. Far beyond the dust cloud, however, New Horizons could observe the sky without much of this interference. Scientists used the spacecraft to measure the total background light of the universe. The idea was elegant. Even galaxies too faint to see directly still contribute light to the overall cosmic glow. If the universe truly contained 2 trillion galaxies, that hidden population should create a measurable brightness across the sky. When researchers analyzed the data, they found something unexpected. The total background glow appeared lower than the 2 trillion galaxy estimate predicted. Instead of requiring vast numbers of unseen galaxies, the measurements suggested that the total population might be much closer to a few 100 billion galaxies. In other words, the older estimate could be closer to reality than the newer one. Suddenly, astronomers found themselves with 2 competing answers. One method suggested around 200 billion galaxies. Another suggested around 2 trillion. The difference between them was an entire order of magnitude. This disagreement highlights something important about science. Popular culture often portrays scientific knowledge as a collection of final answers. In reality, science is a process of continual refinement. Astronomers are not arguing because they are confused. They are arguing because they are exploring the frontier of human knowledge. Both approaches rely on sophisticated methods and reasonable assumptions. Both are supported by evidence, and both may contain part of the truth. The exact number of galaxies remains uncertain because the universe is extraordinarily difficult to measure. We are trying to count objects scattered across billions of light-years of space, while observing only the faint light that reaches us after traveling for billions of years. The uncertainty itself is profound. The difference between 200 billion and 2 trillion galaxies is not a minor discrepancy. The gap between those estimates contains more galaxies than humanity imagined existed throughout most of the 20th century. It is a reminder that even today, despite all our technology and knowledge, much of the universe remains hidden from view. Every new telescope, every new spacecraft, and every new observation has the potential to reveal a cosmos larger and stranger than we currently imagine. And as astronomers continue pushing deeper into space and further back in time, the true number of galaxies may once again surprise us all. At this point in our journey, we need to confront a strange truth. The difficulty in counting galaxies is not simply a problem of technology, It is a problem built into the very nature of the universe itself. Even if we had a perfect telescope, one capable of detecting every photon of light that reaches Earth, we still could not see everything. There are regions of the cosmos forever hidden from us. The reason comes down to two simple facts. The universe has a finite age, and light travels at a finite speed. The universe is approximately 13.8 billion years old. That means light has only had 13.8 billion years to travel since the beginning of cosmic history. Anything whose light has not had enough time to reach us remains invisible, not because it does not exist, but because its information has not yet arrived. This limitation creates what astronomers call the observable universe. Everything we can see lies within this cosmic horizon. Everything beyond it is hidden. If a galaxy exists beyond that boundary, no telescope can observe it today because its light simply has not reached us yet. The observable universe is therefore not the entire universe. It is only the portion accessible to observation. This distinction is incredibly important. When scientists estimate hundreds of billions or trillions of galaxies, they are speaking only about the observable universe. They are not counting whatever lies beyond the horizon. And here, the story becomes even stranger. Most people assume that because the universe is 13.8 billion years old, the observable universe should have a radius of 13.8 billion light-years. That seems logical. If light has been travelling for 13.8 billion years, shouldn't the farthest visible objects be 13.8 billion light-years away? The answer is no, because while light has been travelling, space itself has been expanding. The galaxies that emitted that ancient light have not remained stationary. They have continued moving farther away as the universe expanded. When astronomers account for this expansion, they find that the observable universe is actually about 93 billion light-years across. It is a sphere so vast that ordinary numbers begin to lose meaning. Imagine a sphere 93 billion light-years in diameter. Inside that sphere exist all the galaxies we can observe. Every galaxy counted in deep field images, every galaxy detected through gravitational lensing, every galaxy measured through redshift surveys, every galaxy included in estimates ranging from 200 billion to 2 trillion. They all exist within this observable bubble. Yet, beyond that boundary, the universe almost certainly continues. The horizon is not a wall, it is not an edge. It is simply the limit imposed by time and the speed of light. This leads to one of the most beautiful and unsettling facts in astronomy. We never see distant galaxies as they are right now. We see them as they were when their light began its journey. A galaxy located 1 billion light-years away is seen as it existed 1 billion years ago. A galaxy located 10 billion light-years away appears as it existed 10 billion years ago. The farther we look, the farther back in time we travel. Astronomers often say that telescopes are time machines, and this is exactly what they mean. Every observation is a glimpse into the past. Think about what that means for galaxy counting. The galaxies visible in deep field images do not all belong to the same moment in cosmic history. Some are relatively nearby, and therefore relatively recent. Others are so distant that they appear as they existed when the universe was only a fraction of its current age. A single image contains galaxies from countless different eras. We are not taking a census of one universe frozen in time. We are looking at a layered history of cosmic evolution stretching across billions of years. This brings us to another challenge. Galaxies themselves are constantly changing. When most people hear the word galaxy, they picture something like the Milky Way or Andromeda, a magnificent spiral with graceful arms wrapping around a bright central core. These are indeed among the most beautiful structures in the universe. The Milky Way contains somewhere between 100 billion and 400 billion stars. Andromeda may contain around 1 trillion. Yet these giant spirals are not typical. In fact, they may be the exception rather than the rule. Most galaxies in the universe are dwarf galaxies. These are much smaller systems, containing anywhere from a few million to a few billion stars. Compared to giants like the Milky Way, they are tiny. They are also faint, making them extremely difficult to detect across large distances. A dwarf galaxy that is easy to observe nearby might become completely invisible if placed far enough away. This is one reason galaxy counts remain uncertain. The smallest galaxies are also the most numerous, and they are often the hardest to find. Astronomers classify galaxies into several major categories. Spiral galaxies, like the Milky Way, possess rotating disks filled with stars, gas, and dust. Their elegant spiral arms are sites of active star formation, glowing with young blue stars and pink nebulae. Elliptical galaxies are very different. They appear as smooth, rounded collections of older stars with little ongoing star formation. The largest ellipticals are among the most massive objects in the universe, often occupying the centers of giant galaxy clusters. Lenticular galaxies occupy a middle ground, possessing disks but lacking prominent spiral arms. Then there are irregular galaxies, chaotic systems with no obvious structure, often shaped by gravitational interactions with neighboring galaxies. These categories help astronomers organize the enormous variety of galaxies found throughout the cosmos. Yet even this classification system struggles at the smallest scales. Some objects sit right on the boundary between galaxy and star cluster. They contain only a few thousand stars. Others may be dominated by dark matter, despite having very little visible matter. Deciding whether such objects qualify as galaxies can be surprisingly difficult. The answer matters because including or excluding these tiny systems significantly affects estimates of the total galaxy population. Dark matter plays a central role in this discussion. Galaxies are not simply collections of stars. They exist within massive halos of dark matter, an invisible substance that does not emit light but exerts gravity. In fact, dark matter outweighs ordinary matter by several times. Without it, galaxies would not form the way they do. The presence of a dark matter halo is often what distinguishes a true galaxy from a simple cluster of stars. Yet, because dark matter cannot be seen directly, identifying these halos becomes another challenge in determining exactly what should be counted. The complexity increases even further when we consider how galaxies evolve. The universe does not preserve galaxies in their original form. They grow, collide, merge, and transform. The Milky Way itself is the product of numerous ancient mergers. Throughout its history, smaller galaxies have fallen into it and been absorbed. Streams of stars left behind by these events still orbit within our galaxy today, providing evidence of past collisions. And this process continues. Our nearest major neighbour, Andromeda, is moving toward the Milky Way. Although the collision will not occur for roughly 4 to 5 billion years, it is already inevitable. The two giant spiral galaxies are destined to merge into a single larger galaxy. When that happens, the number of major galaxies in our local region will decrease by 1. 2 galaxies will become 1. This kind of event occurs throughout the universe. Small galaxies merge into larger ones. Large galaxies merge into even larger systems. Over cosmic time, the total number of galaxies tends to decrease while their average size increases. The early universe was crowded with many more small galaxies than exist today. As billions of years passed, those small systems gradually combined into fewer but larger structures. This creates a fascinating complication. When astronomers count galaxies in deep field images, they are counting galaxies from many different periods of cosmic history. Some of the galaxies seen in the distant past have already merged together by the present day. They no longer exist as separate objects. Therefore, the number of galaxies that existed billions of years ago is not the same as the number that exists today. A galaxy census becomes difficult because the population itself changes over time. Adding to these challenges is a problem much closer to home. Our own galaxy gets in the way. The Milky Way is a flattened disk filled with stars, gas, and dust. Because we live inside it, large portions of the sky are obscured by this material. Astronomers call the most heavily obscured region the zone of avoidance. In this part of the sky, dense clouds of dust block our view of distant galaxies. For decades, entire sections of the universe remained hidden behind the Milky Way's disk. Modern infrared and radio observations have allowed astronomers to peer through some of this obscuration, revealing galaxies previously concealed behind the dust. Nevertheless, the challenge remains significant. We are attempting to map the universe while living inside a galaxy that partially blocks our view. Then there is the issue of confusion. In deep astronomical images, not every point of light is a galaxy. Some are stars within the Milky Way. Others are quasars, the brilliant centers of distant active galaxies. Some faint smudges represent single galaxies. Others are multiple galaxies blended together because they are too distant to resolve individually. Distinguishing among these possibilities requires careful analysis and often additional observations. Every deep image contains mysteries that must be untangled before accurate counts can be made. Taken together, these challenges explain why galaxy counting remains one of the most difficult tasks in astronomy. We are limited by the speed of light. We are limited by cosmic expansion. We are limited by distance, by dust, by the faintness of small galaxies, by the changing nature of galaxies over time, and by the simple fact that much of the universe remains beyond our horizon. Yet despite all these obstacles, humanity has managed to estimate the number of galaxies across a region 93 billion light-years wide. That achievement alone is extraordinary. A species living on a small planet orbiting an ordinary star has learned how to count structures scattered across billions of light-years of space and billions of years of time. We have not reached the final answer, but we have come astonishingly far. And as our instruments continue improving, the universe keeps revealing new surprises. Every deeper observation uncovers galaxies that previous generations could not see. Every improvement in technology pushes the cosmic frontier farther outward. The question is no longer whether there are more galaxies waiting to be discovered. The question is how many more remain hidden in the darkness beyond our current reach. And as we will see next, the earliest galaxies of all, the first galaxies ever formed, may hold the key to understanding just how crowded the universe truly is. To understand how many galaxies exist, we must first understand where galaxies came from. There was a time when none of them existed. No Milky Way, no Andromeda, no giant galaxy clusters. No stars, no planets, no black holes. If we travel back far enough into cosmic history, we arrive at a universe that would be almost impossible to recognize. Shortly after the Big Bang, the universe was an expanding sea of energy and particles. As it cooled, simple atoms formed, mostly hydrogen and helium. But even after atoms appeared, the universe remained dark. There were no stars to shine, no galaxies to illuminate the void. Astronomers call this period the Cosmic Dark Ages. For millions of years, the universe was filled with darkness. Yet this darkness was not perfectly uniform. Tiny fluctuations existed within the distribution of matter. Some regions were slightly denser than others. The differences were incredibly small, but gravity does not need large differences to begin its work. Over time, these slightly denser regions attracted more matter. As more matter gathered, gravity became stronger, drawing in even more material. These tiny imperfections would eventually become the seeds from which every galaxy in the universe would grow. One of the most important discoveries in modern astronomy is that we can actually see evidence of those primordial fluctuations. Across the sky exists a faint glow known as the cosmic microwave background. This radiation is the oldest light we can observe, a relic from when the universe was only about 380,000 years old. When astronomers map this ancient light, they find subtle temperature variations scattered across it. Some regions are slightly warmer, some slightly cooler. These variations correspond to the density fluctuations that existed in the young universe. They are the fingerprints of the structures that would eventually become galaxies, galaxy clusters, and the enormous cosmic web stretching across space today. Invisible within this process was something even more mysterious: dark matter. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light. We cannot see it directly. Yet its gravitational influence dominates the universe. In fact, there appears to be far more dark matter than ordinary matter. Long before stars and galaxies formed, dark matter began collapsing into vast halos. These halos acted like invisible scaffolding. Ordinary gas fell into them, collecting in their centers. Without dark matter, galaxies might never have formed at all. The visible universe we know today owes much of its existence to something we still do not fully understand. As gas accumulated inside these dark matter halos, it became denser and hotter. Eventually, conditions grew extreme enough for nuclear fusion to ignite. The first stars were born. These were not ordinary stars like our Sun. They were likely enormous, extremely hot, and incredibly bright. Many may have been hundreds of times more massive than the Sun. Because they were so massive, they burned through their fuel rapidly and died young. Yet during their brief lives, they transformed the cosmos. Inside their cores, they forged heavier elements. When they exploded, those elements were scattered into space, enriching the universe with the raw materials needed for future generations of stars, planets, and eventually life itself. As more stars formed, the first galaxies began to emerge. These early galaxies were very different from the majestic spirals we see today. They were small, chaotic, and irregular. They contained young stars forming at extraordinary rates. They collided frequently. They merged constantly. The early universe was a crowded and violent place. Over billions of years, these primitive structures combined to create the larger galaxies we observe in the modern cosmos. One of the most important events in cosmic history occurred during this period. As the first stars and galaxies ignited, they flooded space with intense ultraviolet radiation. This radiation gradually transformed the universe. During the Dark Ages, neutral hydrogen gas filled much of space, making it difficult for light to travel freely. The radiation from the first stars began stripping electrons from these hydrogen atoms, a process known as reionization. Over time, bubbles of transparent space expanded around young galaxies. These bubbles grew larger and eventually merged together until most of the universe became transparent. The cosmic fog lifted. Light could travel freely across enormous distances. The universe as we know it today began to emerge. For decades, astronomers wanted to observe these first galaxies directly. The problem was that they were unimaginably distant. Their light had traveled for more than 13 billion years before reaching us. Furthermore, the expansion of the universe stretched their light from visible wavelengths into the infrared. By the time it arrived, much of it was invisible to telescopes designed primarily for visible light. The earliest galaxies remained hidden. Then came a revolutionary instrument, the James Webb Space Telescope. Launched in late 2021, the James Webb Space Telescope represented one of the most ambitious scientific projects ever undertaken. Its golden mirror, far larger than Hubble's, was designed specifically to collect faint infrared light from the early universe. Webb was built to see what Hubble could not. Astronomers hoped it would reveal the first generations of galaxies. What they did not expect was how surprising those galaxies would be. Almost immediately after beginning operations, Webb started breaking records. It discovered galaxies farther away than any previously observed. Some of these galaxies appeared only a few 100 million years after the Big Bang. To put that into perspective, the universe is approximately 13.8 billion years old. These galaxies existed when the cosmos was only about 2% of its current age. Yet the real surprise was not simply their existence, it was their maturity. Many early galaxies appeared brighter, larger, and more developed than theoretical models predicted. Astronomers expected the first galaxies to be small and primitive. Instead, Webb found systems that seemed to have formed stars at astonishing rates. Some appeared far more massive than they should have been so soon after the beginning of cosmic history. This created excitement throughout the astronomical community. Scientists love discoveries that challenge expectations, because such discoveries often lead to deeper understanding. The early universe was not behaving exactly as predicted. Galaxies seemed to be growing faster and evolving more rapidly than many models suggested. The universe was revealing new layers of complexity. Webb also discovered strange objects nicknamed little red dots. These compact, intensely red sources appeared in large numbers throughout the early universe. Their true nature remains uncertain. Some may be rapidly growing galaxies. Others may contain supermassive black holes feeding at extraordinary rates. Whatever they are, they remind us that the cosmos still holds many secrets. And this brings us back to the central question of our journey. How many galaxies are there? Every time humanity builds a better telescope, the answer changes. Galileo revealed that the Milky Way consisted of stars. Hubble proved that other galaxies existed. Deep field observations uncovered thousands of galaxies in tiny patches of darkness. Models suggested trillions of galaxies. New measurements challenged those estimates. Webb pushed the frontier even farther, discovering galaxies from the earliest epochs of cosmic history. The pattern has remained consistent for centuries. The deeper we look, the more we find. There is another way galaxies reveal themselves across cosmic distances. At the centers of most large galaxies lie supermassive black holes. These objects contain millions or billions of times the mass of the Sun. Normally, black holes are difficult to detect because they emit no light. However, when gas falls toward a supermassive black hole, it forms a rapidly rotating disk. Friction heats this material to extraordinary temperatures, causing it to shine brilliantly. The result is known as a quasar. Quasars are among the brightest objects in the universe. A single quasar can outshine all the stars in its host galaxy combined. Because of this extreme brightness, quasars can be observed across enormous distances. They act like cosmic lighthouses, revealing galaxies that would otherwise remain hidden. Some of the most distant quasars come from a time when the universe was less than 1 billion years old. Their existence presents another puzzle. How did black holes become so massive so quickly? The question remains unresolved, yet every newly discovered quasar confirms the presence of another galaxy in the early universe. Meanwhile, enormous galaxy surveys have been mapping the cosmos on unprecedented scales. Rather than focusing on tiny, deep fields, these projects chart millions of galaxies across vast regions of the sky. Together, they reveal the large-scale structure of the universe. Galaxies are not distributed randomly. Instead, they form an intricate network known as the cosmic web. The cosmic web is one of the most beautiful structures ever discovered. Galaxies gather into clusters. Clusters connect through long filaments stretching across hundreds of millions of light years. Between these filaments lie immense voids where very few galaxies exist. When astronomers map the positions of millions of galaxies, the universe begins to resemble a giant web or a network of interconnected threads. Gravity and dark matter shaped this structure over billions of years. Our own Milky Way occupies a small corner of this web. It belongs to the Local Group, a collection of dozens of galaxies dominated by the Milky Way and Andromeda. The Local Group itself is part of a much larger structure known as Laniakea, a supercluster containing the mass of roughly 100,000 galaxies. And even Laniakea is only a tiny piece of the observable universe. Now consider the numbers involved. Suppose the observable universe contains only 200 billion galaxies. Even that conservative estimate is almost impossible to comprehend. If each galaxy contained, on average, 100 billion stars, the total number of stars would be a 1 followed by more than 20 zeros. Some estimates reach even higher. Astronomers often compare this figure to the number of grains of sand on Earth. There may be more stars in the observable universe than grains of sand on every beach and every desert on our planet combined. And around many of those stars orbit planets. Modern astronomy has revealed that planets are common. Most stars appear to host planetary systems. This means that the number of worlds in the observable universe is truly staggering. Trillions upon trillions of planets likely exist. Some are rocky, some are gaseous, some may possess oceans, some may have atmospheres. A small fraction could potentially support life. This realization leads naturally to one of the deepest questions humanity has ever asked. If there are hundreds of billions or trillions of galaxies, and if each galaxy contains billions of stars and countless planets, where is everyone? Why does the universe appear silent? We do not yet know the answer. Life may be common. It may be rare. Intelligent civilizations may arise frequently or almost never. The truth remains hidden. Yet perhaps the most astonishing part of the story lies beyond the observable universe itself. Everything we have discussed, the galaxies, the stars, the cosmic web, the deep field images, the quasars, the black holes, exists within the observable universe. But the observable universe is almost certainly not the whole universe. Beyond our cosmic horizon lies a region we cannot see. The universe does not appear to end at the edge of visibility. Instead, visibility ends while the universe continues. How large is the entire universe? The honest answer is that nobody knows. Measurements suggest that space is remarkably flat. A perfectly flat universe could be infinite. It could stretch forever in all directions without boundary or edge. Alternatively, it could be finite, but so enormous that its curvature remains undetectable. Current observations cannot distinguish between these possibilities. If the universe is finite, then the total number of galaxies may simply be far larger than anything we can observe. If the universe is infinite, then the implications become almost impossible to grasp. An infinite universe would contain an infinite number of galaxies, no final count, no largest number, no end. The answer to our question would not be 200 billion or 2 trillion, it would be endless. And that possibility carries a strange beauty. We began this journey asking how many galaxies exist. Along the way, we discovered that the answer depends on what we mean by exist. Are we counting only the observable universe? Are we including galaxies too faint to detect? Are we counting galaxies that existed in the past but have since merged? Or are we considering regions forever beyond our horizon? Within the observable universe, the most honest answer today is a range, somewhere between a few hundred billion galaxies and perhaps 2 trillion or more. Future observations may refine that estimate. New telescopes may uncover hidden populations. The number may rise, it may fall. But whatever the final answer becomes, it will represent one of humanity's greatest achievements. Think about how far we have come. Our ancestors once believed the Milky Way was the entire cosmos. Then telescopes revealed stars beyond counting. Hubble showed that Andromeda was another galaxy. Deep field images exposed thousands of galaxies in apparently empty darkness. New Horizons measured the faint glow of the cosmos. James Webb revealed galaxies from the dawn of time. Generation after generation, humanity pushed farther into the unknown. No single person counted the galaxies. It took centuries of effort, thousands of scientists, thousands of engineers, countless nights of observation, telescopes on mountaintops, spacecraft traveling billions of miles, mirrors polished to incredible precision, mathematics developed across generations, all working together to answer one simple question: how much is really out there? And perhaps the most extraordinary fact of all is this: among all those galaxies, among all those stars, among all those planets scattered across the observable universe, there is only one place where matter has been confirmed to wake up, become conscious, and ask that question. That place is Earth. We are a small species living on a small world orbiting an ordinary star in one galaxy among hundreds of billions. Yet from this tiny corner of the cosmos, we have learned to measure the age of the universe, trace the growth of galaxies, map the cosmic web, and peer almost all the way back to the beginning of time. The galaxies themselves do not know they are being counted. The stars do not know they are being observed. The universe simply exists. But we are here. We are the observers. We are the counters. We are the beings who looked up into the darkness and refused to stop asking questions. So the next time you stand beneath a clear night sky and see the faint glow of the Milky Way stretching overhead, remember what lies beyond it. Beyond those stars are other galaxies. Beyond those galaxies are countless more. Beyond them lies a universe so vast that even our greatest numbers struggle to describe it. And beyond the limits of what we can see may lie an even larger reality, waiting forever outside our horizon. The true number of galaxies may be hundreds of billions, it may be trillions, it may be infinite. But the fact that a conscious species exists to wonder about that number at all may be the rarest and most precious thing in the entire cosmos. Thank you for joining this journey across the universe, from the first stars to the farthest galaxies, from the dawn of time to the edge of observation. And tonight, as you rest beneath the stars, remember that above your roof, beyond the clouds, beyond the planets, beyond the Milky Way, there stretches an ocean of galaxies blazing across the darkness. All of it is real. All of it is out there. And we are fortunate enough to live in the age when we can still see it. The end.